Here's a walkthrough of the post-lab calculations for the gases lab. First, we have to figure out the mass of the reagent that we used, and we have to look at our balanced reaction. So in the lab that we did, we took a compound called potassium chlorate, and it was mixed with a catalyst, which is not part of the reaction itself, and then we just added some heat. And so that iron oxide that you saw in the tube, that wasn't participating in the reaction. It was the potassium chlorate that we were interested in. And the products of the reaction were potassium chloride and oxygen gas. And so we're going to need this balanced equation. And then we are also going to need a little bit of information about our compound. So our potassium chlorate is 122.5, I believe, grams per mole. And we used 0.300 plus or minus 0.002 grams. Now, when you are calculating the moles of potassium chlorate used in the reaction, then you don't need to take into account that 0.002, but this will become important when we go to talk about our error analysis as in our last question of our post lab. So we just kind of want to keep this in mind, that the error in weighing out our product is very, very small. Okay, so it likely is not going to be the main source of error for your calculations. But now that we've made a note of this, we are going to use this only going forward. And so let's take a look. We have, first off, we need to know how many moles of potassium chlorate we used. So this is our first question right here, is what was the mass? And then we convert this to grams. I'm sorry, we convert grams to moles. So we have 0.3 grams of potassium chlorate, and then we multiply by 1 mole over 122.5 grams. So this means that we take 0.3 and divide by 122.5, and we get 0.00, and then I'm going to record 4 digits because I don't want to lose too much data there. And so that's how many moles we have. So the next thing that we have to do is use the stoichiometric coefficients here to figure out how many moles of oxygen gas we can expect to form given the amount of starting the amount of starting reactant that we began the reaction with. And so I'm going to take and set up another ratio here to answer question 3, where I have my moles of potassium chlorate here. And then I want my units to cancel. So I want moles of oxygen, and there are 3 moles of oxygen for every 2 moles of potassium chlorate. So I encourage you, if you're not used to writing them out like this, please do practice this. This is a skill that you will need. You will need to demonstrate this skill on the midterm. You will need to demonstrate this skill on the final. And if you use your units, you're not going to make mistakes when it comes to, do I multiply, divide, whatever. So like we had over here, we canceled out our masses, got moles, and here we're canceling out moles of potassium chlorate. and we take our 0.002449 and multiply it by 3, divide by 2, and we get 0.0036735. And I'm just going to record that, but I know that my last digit that's significant is that 3 right there. Okay. So now my next question is, what is the barometric pressure that you recorded in millimeters of mercury? So our mercury barometer in the hallway showed a reading in millimeters or centimeters, depending on what you recorded, but you can get the recording directly from the barometer in millimeters or centimeters. And I don't remember exactly what it was, so I'm just going to, for simplicity, use 760 millimeters of mercury. And then for 5, you're going to need to convert that to atmospheres. And so this one's really easy for me because I just picked arbitrarily the 1 atmosphere pressure. But what you'll do is take whatever it is that you recorded. So if it's 755 or 761 or whatever that is, then you just convert that to atmospheres by multiplying by this factor. So 1 atmosphere per 760 millimeters of mercury. So you basically take whatever your reading is in millimeters of mercury and divide by 760, and that will give you the pressure in atmospheres. So again, yours will be slightly different. Okay, so then the temperature of the oxygen gas in degrees Celsius, I'm just going to use 20 degrees. It should have been anywhere from 20 to 25 likely when you did the experiment. And so you want to just make sure that you are recording it correctly. And then question 7 asks for it in Kelvin. And so we would just take our 20 degrees Celsius and we would add 273, and then we get 293 Kelvin. And remember, we have to do this because Kelvin doesn't have a negative number as an option on the scale, and we have to look at it in the Kelvin scale every time we're working with gases. All right, so now we have some information here, right? So what do we have so far? We've got moles, and we've got pressure, and we've got temperature. So now we're able to predict the amount of oxygen gas product that we could expect to get. And so in order to do this, we're going to have to use the ideal gas law. PV equals nRT. Our pressure is 1 atmosphere. Our volume is our unknown. Our N is 0.0036735, and I'm going to note that that's my last digit that I know for sure. R is 0.0821, and the units are in liter atmospheres per mole Kelvin. So the nice thing about this gas constant here, and it might look a little confusing, but this is just the unit. And so just like pounds over square inches or something, this is just liter atmospheres over mole Kelvin. And so this reminds you what your units need to be. So liters for the volume, atmospheres for pressure, moles, that's just a number, and then the Kelvin. So you can't use this gas law unless you have your values all in these units. So don't forget to double check that and make sure you're checking that your units are accurate before you report your final answers. Okay, and then lastly, we would use our temperature of 293 Kelvin. And so I'm just going to take these and solve for volume. So I'll have 0.003675. I'm going to multiply that by 0.0821 and 293. And then that all gets divided by 1, which is quite convenient. So then my volume expected was 0.08837, which I'm going to put right there. So 0.0884. And now that's in liters. And then so for question 9, I'm asked to convert that to milliliters. And so remember that 1 liter is 1,000 milliliters. So we want to make sure that we aren't forgetting how to do unit conversions. And so then my answer is 88.4 milliliters. Now, you also collected a volume of water and measured that. And we said that the volume collected was equal to the volume of oxygen produced. And so for 10, you're going to record the volume of water from the 250 ml beaker in your setup that you measured at the end. And that is your experimental amount of gas. So that's the experimental O2 volume. All right, so now error analysis. So this is where it gets a little bit tricky. When we're talking about error analysis, it's not okay to just say human error, because obviously a human likely made the error, but that tells me nothing about what the error could have been. And it also doesn't tell me that you understand how your actions could cause an error to be present in your data. So, for example, we had 0.3 plus or minus 0.002. So let's say that we actually did have 0.302. So instead of 0.300, we started with 0.302 grams of potassium chlorate. And so you can do the calculation again and find what your reaction, like what your experimental or expected would have been. And so if you do that, you're not going to see a significant difference in your answer. So you can kind of go through and do your calculation again if you want. But like when I do that, I get an answer of 88.9 liters, which are milliliters, so 89 instead of 88. That's really, really small, right? And so you want to make sure that if you're off, if you're off by like 10 milliliters, it's not because this was weighed incorrectly. Now, another thing is that if you want to think about perhaps you generated more gas and this means that the water level that you measured so the water level in the beaker was too low. So maybe some gas leaked, or perhaps the gas that went through the tube, like there's that distance that the water had to flow. Maybe all of the water didn't get out through the tube or something like that. So how would that affect your data? Well, if there was more gas produced than you thought, then that means that your answer here would be too low. So for example, let's say that your prediction was that you would get 100 mils. Okay, so we predict 100 milliliters of O2. And we measure it and we get 90. So that means that this would actually make sense. This thought here, this hypothesis would make sense because your water level was too low, which means that what you got in your experiment being lower than what you predicted, that means that like, well, maybe you actually did make enough gas, you just weren't able to measure it. So that would make sense. But if your prediction was 90 and your actual was 100, then this wouldn't work anymore. And so you really need to think carefully about what the error would make your data look like. So I hope that that makes a little bit of sense. If you would like to chat about your error analysis and let me know what you think and look at your data, I'm happy to talk with you about it before you turn it in. Just let me know. This will not be due for another week. It's not due until our next lab. So you've got some time to work on this. And just make sure that you're being very clear in showing all of your work. Every student needs to turn in their own assignment. And you can do all of your calculations by hand. You can either do it on separate paper or you can write it into your